Okay, today we're going to talk about electron configuration. This goes along with our activity that we did yesterday. Where in the heck are the electrons in an element? Well, we can remember rules like the Aufbau principle, Pauli exclusion principle, or the Hund's rule, and we're going to apply those rules, but we're not going to actually memorize what those are. Well, first of all, let's review just a little bit from our previous video. Remember that hydrogen has one proton and one electron that orbits in the first energy shell. And that helium, it's got two protons, two neutrons, and two electrons. And that's atomic number 2. Remember, protons, atomic number equal protons equal electrons, APE. Okay, now this first energy shell can only hold 2 electrons. So we're going to go to the next energy shell, and this is going to be lithium, then beryllium, then boron, carbon, and each time we're adding a proton and an electron. The outer shell is called the valence shell, and the electrons that are in that shell are called valence electrons. Okay, and we can see we have 5 electrons in the outer shell, so that would be nitrogen, then oxygen, fluorine, and finally, when we get to the end of the period, we've got 8 electrons in the outer shell for a total of 10 electrons. And remember that this is the magic number. It's called the octet rule, octet meaning 8. 8 electrons in the valence shell. And so this element is very, very happy. It's got its outer shell filled, so it doesn't bond or doesn't react with other elements, and that whole group is called the noble gases. Okay, and we use this information on valence electrons in the outer shell, to draw what we call a Lewis dot structure. Remember, hydrogen has 1 valence electron. It's in the first group, so it gets 1 dot, just like sodium and lithium. And beryllium is in the second group, so it has 2 valence electrons. It gets 2 dots. Boron, carbon, nitrogen, oxygen, fluorine, and finally neon. The most dots you can have is 8, because once you have 8 dots, that means there's 8 valence electrons. That means that the element's happy and you start a new period. Okay, so if you will go ahead, and we're going to pause here for a second for you to get your periodic tables out, and I want you to look at your periodic table and look across the top, and you're going to see numbers just like here on the video that go from 1A, 2A, and then it skips the 10 in the middle, 3A, 4A, 5A, 6A, 7A, 8A, or it could have Roman numerals depending on which periodic table that you're looking at. If you're looking at the periodic tables on the wall, those are going to have Roman numerals. So we're going to pause here for a moment and talk about that. Okay, well, let's look at this idea of electron configuration now. Where do the electrons fall? And in order to do that, we're going to have to move helium over next to hydrogen. And sometimes hydrogen moves over next to helium. Hydrogen and helium do weird things. So sometimes we move it to the left, sometimes we move hydrogen to the right. And when we do that, we're going to actually block off areas of the periodic table, and we're going to give them names. For example, this block, second block, the third block, and the fourth, and they're called S, P, D, and F. Now when we do electron configuration and we find out where in the heck the electrons live, we're going to follow two simple rules. Okay? And those are read from left to right like you would when you read a book. And you have to pass through each element to get to the element in question. So if you'll please write those two rules down. Okay, now the format for writing electron configuration is we're first going to write the row number. And if you'll look at this periodic table, you'll see on the left-hand side, the rows are numbered 1, 2, 3, 4, 5, 6, 7. And remember, those correspond to how many electron shells the element has. So those on row 1 are just going to have 1 electron shell. Those on row 2 will have 2 electron shells, and so on. After the row number, we're going to write the block number. Okay, and those are the red, the green, and the maroon blocks. And then as a superscript number, we're going to write the number of electrons that that element has. And remember, the atomic number is the number of electrons. So let's start off with hydrogen. Okay, so if we're going to write the electron configuration for hydrogen, we're going to write the row number first. So hydrogen is in the first row. Okay, then the block. And if you remember, that first block is the S block. And hydrogen's atomic number is 1, so that means that it has 1 proton and 1 electron. So on electron configuration, we're just interested in the electrons. So it's going to be the same. It's going to have 1. So the electron configuration for hydrogen is 1s1. Okay, now remember the rules. We read a book from left to right, and we have to remember the elements we pass through to get to the element in question. So now we're going to do helium. So we have to pass through hydrogen to get to helium. So we're going to maintain that 1s1, but now helium, its atomic number is 2. That means it has 2 electrons. So its configuration is going to be 1s2. Okay, so there's no other elements on the first row. So we're going to go down to the second row, lithium. Okay, now remember we have to pass through hydrogen and helium to get to lithium. So lithium's configuration is going to be 1s2. Then we're going to write the new row number 2s, because it's in the S block, 1. Okay, so lithium's configuration is going to be 1s2, 2s1. And if you look at the superscript numbers, the 1 and the 2, and if you add those together, you get 3. And that should equal the atomic number of the element in question. So we're doing lithium here. So you can see that does match lithium's atomic number of 3. Okay, now beryllium, 1s2, because we had to pass through hydrogen and helium, and then 2s2. It's in the second column. Okay, so it's going to be a 2s2. Okay, now let's go to boron. We're introducing a new block here. Up to now, we've just been concentrating on the S block. But see, in the second row, now we have not only an S block, but we have to talk about a P block. So if we go to boron, it's going to be 1s2, 2s2, and boron is the first element in the P block, so it's 2p1. Okay, and there's 6 elements in the P block as you go across the row. So carbon is going to be 1s2, 2s2, 2p2. Nitrogen is 1s2, 2s2, 2p3. Oxygen is 1s2, 2s2, 2p, and it's the fourth element. And let's just make sure we're on the right number. If we take the superscript numbers 4, 2, and 2, that adds up to 8. So let's look at oxygen's atomic number. Oxygen is atomic number 8, so we're in the right place. Fluorine is 1s2, 2s2, 2p5. And finally, neon, which is the end of the second row, 1s2, 2s2, 2p6. Okay, we're going to pause here for questions. Okay, so let's continue on the third period now. Now remember, we have to pass through, we're talking about sodium here, we're going to have to pass through all the elements to get to sodium. So it's going to be 1s2, 2s2, 2p6, and sodium is in the third row, so it's 3. Sodium is in the s block, so it's 3s, and it's the first element, so it's 3s1. Okay, magnesium is 1s2, 2s2, 2p6, 3s2. Okay, now we're going to try to see if you can do this. Okay, we're back, and so aluminum, as we verified, is 1s2, 2s2, 2p6, 3s2, 3p1. Okay, and silicon is 1s2, 2s2, 2p6, 3s2, 3p2. Phosphorus, 1s2, 2s2, 2p6, 3s2, 3p3. Sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. And finally, the end of the third row, 1s2, 2s2, 2p6, 3s2, 3p6. Potassium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And calcium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, now we haven't talked about the next block. We've talked about the S block and the P block, but we haven't said anything about the D block because atomic number 21, scandium, is the first element that's in the D block, and we're really not going to be responsible for anything in the D or F block, but I do want to show you. The D block is higher energy than the S and the P blocks, but the 4S energy shell is lower energy than the D block. So the first row on the D, even though it's in the fourth row, it's higher energy, so it's 3D. But the 4S is even lower energy, so we fill the 4S first, so that's why that block is down even with the ones on the 4. Just remember that scandium, the first D row is 3D. I just remember it like a 3D movie. So 3D is the first row on the D block. And so scandium would be 3D1. Okay, now let's take a really complicated one and let's talk about gold. Okay, so here you see the configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d10. And if you'll count with me, there's 10 elements that are in the D block. 1, 2, 3, 4, 5, 6, 7, 8, 9, and zinc is 10. So that's where you get the 3D10. Then we go back up to 4P6, and then down to the 5th row, 5S2. And we've already done 3D, so the next one would be 4D10. Even though it's in the 5th row, it's 4D10. And then 5P6, and then down to 6S2. And then if we count gold, it's the 9th element over, so it would be 5D9. And when we write electron configuration, for elements that we get deep inside the periodic table, as you can see here, the electron configuration starts to get quite long. So scientists have developed a shorthand, and it's called the noble gas shorthand. And so what we do is we look at, okay, so for gold is on the 6th row. So what we do is we look up at the 5th period, and the noble gas that's on the 5th period is xenon. So xenon ends with 5p6. So we'll put brackets around that part of gold's electron configuration up through xenon, which is 5p6. And what we do is replace that whole entire series of numbers with xenon's symbol, Xe, and then we just tack on the 6th period up to the gold that we're talking about, the 5D9. Okay, so if we were going to look at calcium, or we're going to do a noble gas shorthand for calcium, calcium is 4s2, so we'll look at the 3rd period, find the noble gas on the 3rd period, that would be argon. So argon would be 3p6. We'd put brackets on around the 1s2 all the way to 3p6 and replace that with argon. So calcium's shorthand is argon, Ar, the symbol Ar in brackets, 4s2. Okay, so let's look at magnesium. Okay, what would magnesium's shorthand be? I'm going to pause here to let someone answer. Okay, we're back, and magnesium shorthand would be neon 3s2. Now, the elements in, up to, say, 12 or 18 or 20, the electron configuration doesn't get too long, but if you start talking about elements like gold and mercury and radon or polonium, then it does tend to get quite long, and so that's why we use a shorthand for those.